Good afternoon, I'm Eric. This is Roger, and we are Team Maverick. Inspiration Mars is truly a maverick of the mission in that it's much different, much more ambitious than the other currently proposed interplanetary missions. Christine was able to join us today, but we're all graduate students at the University of Colorado Boulder studying human spaceflight. I hope that any of you who went to Boulder for last year's conference enjoyed your stay. We started this project in the Space Habitat Design course at the University of Colorado. And that course focuses on a triple-faceted design approach, which will guide our presentation today. That design approach starts with a mission statement, which leads to high-level functional objectives and then system-level objectives. We also look at the concept of operations and available technologies to decide on a large-scale vehicle configuration. Then we go on to select individual technologies. Here's our mission statement: to design a conceptual spacecraft for a mission that sends 2 humans to fly by Mars, support their needs in transit, and return them safely to Earth. This leads to our high-level functional objectives: to keep the crew happy, healthy, and alive in transit. We also need to get them out on their way to Mars and return them safely to Earth when they return. Those high-level functional objectives lead to system requirements, which we then split into the classical spacecraft subsystems. The structure subsystem protects our crew from the vacuum of space and the radiation environment, as well as micrometeorites and orbital debris. Our environmental control and life support subsystem provides food, water, and air, and also deals with produced waste. The crew accommodation subsystem provides health, exercise, medical equipment, as well as sleeping arrangements and restraints and entertainment. Our communication system is vital for achieving the inspiration mission of Inspiration Mars. Our propulsion subsystem will get us out onto our path to Mars. It'll perform any corrections on our way out, and it will also perform a potential abort maneuver, which we'll detail later. Power and thermal subsystems will support the rest of our subsystems by generating and storing power and rejecting excess heat. So the mission statement led to our system requirements. Looking at the mission as a whole and available technologies, we were able to arrive at some high-level system architectures. One big constraint we had was the launch vehicle selection, so we chose a launch vehicle first. Then we went on to look at what sort of volumes our crew will need and what sort of launches will be necessary to provide that volume. Just looking at the capabilities and missions performed with current launch vehicles, it's clear that the operational launch vehicles are not appropriate for a mission of this magnitude. So we looked ahead to the upcoming heavy lift launch vehicles, SpaceX Falcon Heavy, and the NASA Space Launch System, SLS. The Space Launch System, we don't think will be human rated in time after an initial flight in 2017, maybe a small human flight in 2020. Whereas the Falcon Heavy, expected to fly next year, could be operational for humans for a mission of this magnitude in time. So we chose the Falcon Heavy and based our further designs off of that. Then we went on to consider how many launches we should do. We could use a single Falcon Heavy launch directly onto a Mars trajectory, but that design would be severely mass limited. You can also do multiple launches, dock in low Earth orbit, and that option increases the amount of mass we can bring up. So we looked at some initial architectures. Here's our initial look at a single launch architecture. It's safe because it avoids the debris environment of Earth, but there's not a lot of space inside. We also looked at a much bigger option with 3 launches. It's much more spacious inside, but it's more expensive and more dangerous with all that docking in LEO. So we decided on a 2-launch design sort of best of both worlds. It doesn't have it. It's more spacious than the single launch option, but less dangerous than the dual launch option. So we chose that two launch option and iterated on that design to arrive at our final architecture, which includes the Falcon Heavy upper stages as an integral part of our system. I'll detail that system by looking at the mission summary. So we'll launch in late December 2017, perform our trans-Mars injection burn on January 5th. Once we leave the near-Earth environment, we'll deploy our habitat, begin our science and outreach mission. As we approach Mars, we'll perform any trajectory corrections, and then we'll have that one-day Mars flyby, where the cruise day will be significantly different. After that, we will return to Earth, and we will re-enter and land. So here is a close-up view of that launch phase. First, the cargo vehicle will launch. Once that checks out, we'll launch the crew up on another vehicle. They'll dock in low Earth orbit before performing the trans-Mars injection burn. Here's what those modules look like during launch. They're designed specifically to fit inside the Falcon Heavy payload fairing. The crew launch carries a Dragon capsule for re-entry upon Earth return, and it also carries 7 metric tons of abort fuel. Here's what the vehicles look like once they're docked with stored inflatables. So once they've docked, we perform the trans-Mars injection burn, first by burning one of their engines, and then rotating about using the attitude control system and performing a second burn. Then they'll deploy their habitat, the inflatable modules, solar panels, radiators, and antennas, and begin their science and outreach mission. Here's what the vehicle looks like in transit. The radiators are not pictured. Let's take a look inside. Working our way down from the top, we've got we've blocked out volumes of our subsystems to get a feel for how much space our crew will have in transit. That's enough food to last the crew for the entire duration, as well as enough water to start the water recycling system. 3 large crew accommodations blocks contain the exercise, health equipment, sleeping provisions, disposable clothes, so on. The cargo module, which is on the upper one, will house our primary Eclipse system, while the crew module will take advantage of the built-in Eclipse on the Dragon capsule. Waste will be stored around the Dragon capsule to increase radiation protection. This is where the crew will go in the event of a solar event. All this comes out to 90 cubic meters of habitable volume, which is a little bit bigger than my studio apartment. During transit, the crew will be doing lots of things. I think it's good to have an unstructured day so they can do things when they want to, but on average, they'll be doing these activities for those hours per day. They'll be sleeping for up to 8 hours a day. They'll be maintaining their health with exercise and eating and with meals. Be taking care of the craft, talking to ground control. In their free time, they'll be talking to friends and loved ones back home, entertaining themselves, and doing some personal development, learning new skills. The science mission is very important. The main science objective will be the crew themselves, studying how they react to the environment of space. They'll be breaking the record for longest time in space by 60 days, so we'll be collecting vital information for future long-term space missions. We'll also have a plant growth experiment to provide some fresh food and boost morale. Another big objective of Inspiration Mars is inspiring the world, and that will be accomplished through outreach, talking to the general public, talking to school children, letting everyone know how it is up there. So as they approach Earth, the vehicle will separate. The crew will be inside the Dragon capsule. They'll perform an aero capture maneuver to enter a closed orbit with Earth. They'll wait for at least one orbit before re-entering and landing in the ocean. They'll move to the Dragon capsule, and the rest of the spacecraft will burn up in the atmosphere.
Hi, my name is Roger, and I'll be talking about the abort scenario, as Eric mentioned, as well as the subsystems definitions from component levels, and then the cost and scheduling analysis that we've done. So, in our abort scenario, we've allowed for fuel up to 2 kilometers per second delta V. What that means here in the upper right corner, that plot will show the return duration after the, if an abort scenario is selected within the first 51 days. So in that first part of the graph, those are the first 51 days to decide whether or not to abort flying by Mars. Now, the graph shows that the return time is still almost 300 days. So that 300 days plus the 51 days that they've already traveled will take you to about a year. So they'll still be spending about a year in travel. Now, the empty spots in this graph show the areas during the mission where you cannot abort. So the amount of fuel isn't sufficient to return you to Earth. You'll notice that after that 227-day mark, there are opportunities to fire the abort fuel and return to Earth, but I'll go over why that's not really a great idea. So, as everybody's seen already, this is the nominal trajectory off to the left side. The astronauts will fly by Mars at 227 days and then return at 501 days. So in the abort scenario, they would abort at 51 days and then return to Earth almost a year later. In the abort configuration, they would lose more than half of the habitable volume they have. So this is why it's not a great idea to, after flying by Mars, ditch everything and run home. Because they'll only save about 25 days and they'll lose approximately 60% of their habitable volume. So now I'll go over the specific subsystem components as Eric detailed before. So once again, there are structures, eclipse, crew accommodations, avionics, communications, propulsion, power, and thermal. So in our structure subsystem, we're mainly concerned with providing sufficient radiation protection. So in doing so, we have outlined the inflatables to be layered Kevlar, which is in development by Bigelow, that will become rigid after deployment. And the whole material will be layered with aluminum, low-density polyethylene, and titanium, which is thought to, again, provide a little bit more radiation protection. We will also have a water line inside these layers to provide for more radiation protection. In the ECLIS subsystem, this is mainly proven technologies that are in use on ISS or being tested in ISS. So we have the air, water, food, and waste subsystems. Now what's special about ours is in our waste, we have, our waste subsystem, we have designated for a compactor to be used to compact metabolic as well as packaging waste, and that to be packaged and used as additional radiation shielding around the Dragon capsule. In crew accommodations, we are providing for the provisions for clothing, housekeeping, sleep, personal storage, crew health, and hygiene and waste, as well as equipment for the operations and maintenance upon the spacecraft, which we think will be extensive, given the long nature of the mission. In avionics and communications, we will be communicating with Earth. We've designed to be able to stream to Earth, which actually means there's a significant delay, up to 8 minutes at the longest part of the mission. So the network that we're going to be using is NASA's Deep Space Network that we'll be renting out on the ground, and then we have 2 antennas on board to send signals and receive signals. During the Mars flyby, as other groups have mentioned, there's an eclipse period, so we have We have hard drives on board to accommodate for video storage and picture storage so that the crew can return valuable pictures and videos from the actual flyby. So in our propulsion system, this is mainly outlined in the abort scenario, but we've added up the abort fuel mass as well as the associated plumbing. And we're using the same engine for the upper stage engine from the Falcon Heavy, so we don't need to redesign anything. In power, we've done this in an interesting way, in such that we've designed to a solar flux. And that red line on that graph shows about 1,200 meters, or 1,200 watts per meter squared, and throughout the mission profile. So as you can see from this mission profile, there are some periods in which we have excess energy and some periods in which we're deficient in solar energy flux. To accommodate for the deficient periods, we will be utilizing battery storage upon the spacecraft. The thermal control unit is very similar to the ISS current unit. We'll be using a single-phase exterior loop system and a water-cooled interior loop system. So when we did a comparison for our subsystems, we interpolated the data given from past spacecraft, so like the ISS, the shuttle, the Gemini, and Apollo missions. We took their mass percentages per subsystem and we broke it down, and we said, well, if we have a spacecraft of the mass that we're designing, what percentage and how much mass should be dedicated to each subsystem. So that gave us our top-down mass analysis, so that's given in the blue bars. And the bottoms-up mass analysis is given in the red. So a close correlation tells us that our design is realistic, and it gives us an idea that we're on the right track. In that same kind of idea, we were looking at the spacecraft density comparison. Now this isn't a true density comparison, but it's a mass per habitable volume. So we looked at previous spacecraft and projected spacecraft. So the ISS and Orion both are non-inflatable, and they don't have inflatable components, so they have a higher ratio of mass to habitable volume, whereas the trans-hab and beam structures have far less. Now we sit somewhere in the middle, which is expected since we are utilizing both. So from there, we did a cost analysis based on the scheduling, so these two are tied together. We did a bottoms-up approach for cost estimation in terms of materials cost and personnel cost. So the total cost summary, we are projected to spend approximately $1 billion throughout 2019, which is the life of the mission. And then we have a peak cost of about $450 million in the year 2016. Now, these numbers are dictated by the schedule in such that we think the most design and manufacturing will occur during 2015 and 2016, and of course this year. But the integrations and testing and assembly and preparation will occur in 2017, 2018 as we approach launch. So in summary, we have a mission design that will incorporate 2 Falcon Heavy launches that will give a crew of 2 approximately 45 meters cubed per person and have a total dry mass of about 19 metric tons. Now that includes the abort fuel, and then and that leads me to our key features, which we are able to abort the mission up to 51 days after the Earth escape, so that reduces the risk in terms of undertaking such a long mission that has never been done before. We also have multiple radiation protection features, such as the waste radiation barrier and the waterline walls, and we can utilize the upper stages of the Falcon Heavy propulsion vehicle to orient such that it defends against solar events as well. We have also chosen for designs that are already in use or in high levels of development, such that we will get a reliable design out of it. And we'd like to thank our advisors, Dr. Dave Klaus and astronauts Joe Tanner and Colonel Jim Voss for their guidance, as well as our department and the William F. Marlar Foundation for lending assistance.
you say you have 2 kilometers a second of delta V for the abort option. Can you use that shortly before Earth re-entry in order to reduce the entry velocity?
Yes.
So then you're saying you can reduce the entry velocity from the canonical 14 point something to 12 point something?
Yes, the idea would be that we would incorporate aero capturing, but if, since one of the issues that we came up with is, are we able to fire it after 500 days of travel, right? I mean, it's really not something that's been tested yet, so we don't know. But if it is able to, then yeah, we can retrofire and then slow down the velocity of the craft even more before we enter.
You have liquid oxygen,
Yes.
the column.
Mhm.
What about the boil off for 520 days?
So the boil off we have calculated for 51 days, and the amount of the mass of liquid oxygen that we've allotted for will accommodate for up to 51 days. But beyond that, we didn't truly do the full calculation for the entire 501-day mission.
But what is your rate of boil off after 51 days? How much has boiled off?
It should be the standard 0.05% boil off, but we haven't done
Over
that.
51 days? Or per day?
Oh, per day.
Okay,
So
so
that's
that's
a standard
1%
boil-off.
every 20 days.
Mhm.
They're claiming 1% boil off every 20 days. It's 1%. So every 200 days, 10%. Well, it's 25%, they would still have some. They're claiming a 20th of a percent per day boil off, which means 1% every 20 days, 10% every 200 days.
The pre-entry burn is something we haven't looked in depth into, but it is an added benefit of carrying this fuel with us.
Plus you get shielding out of it.
Yes.
You didn't use the SLS because it wasn't going to be human rated in time, but you also then didn't have launch abort in your scenario that I can tell. Is that correct?
As in the actual launch day aborting?
Yes.
During launch.
During launch, there's no launch abort option.
We didn't accommodate for that, but given if the Falcon Heavy becomes human rated, then we can consider doing a day of launch abort as well.
What does that mean?
Say that.
So it would be the standard propulsion like bounce off system where the SLS is considering, where they have rockets at the front of the rocket that will pull the crew capsule away.
But you're configured such that you can't pull the crew capsule away because you nestled the Dragon inside under the bearing.
Right, so that would require some redesign.
What was your choice for the life support system?
In terms of the Eclipse components.
Yeah, the mechanisms.
Okay, so this one for the air subsystem, we're utilizing this body air electrolyzer. We understand that the pyrolysis reaction can be utilized, but we didn't feel it was ready because it will produce many harmful toxins when you're burning methane without oxygen. So we didn't want to include that in our final design. For water, particulate filters, activated carbon, ion exchange, these are all technologies that are or have been tested on ISS, and
But it's not fully closed, so you
Right,
add
so-
in your mass statement whatever you need to make up.
right. So in Eclipse, we've accommodated for 90% recovery of water, and we're bringing along the necessary makeup.
How are you treating the urine?
In brine evaporation, so that's a technology that's in development right now by NASA. Yeah.
That needs to be the last word. Thank you.